Hi, everyone. I'm Venu, and I'm an assistant scientist at Gemini South. I would like to begin to thank the organizers for this opportunity and also to apologize in some small fashion because of the ambiguous nature of my title and abstract. In my defense, when we submitted this abstract, it was because we had just received Zoro data of R136, and we weren't sure we could process and reuse it in time for the talk, but we have. And I think the data looks spectacular, but I think the audience will be the real judge of how the data look. So our story begins on a summer night around a year ago at Cerro Pachon. We used Zoro, which is located inside the GCAL unit, the speckle imager that covers around 2 arcsecond field of view, to image the Large Magellanic Cloud. Now, the Large Magellanic Cloud is a dwarf galaxy around 50 kiloparsecs away, at around half a solar metallicity. Like many dwarf galaxies, it doesn't have a very active center of star formation, but there is a lot of star formation happening within it. And there is especially a lot of active star formation going on in the 30 Doradus region, which can be seen at the top center of this image. And that is where our target lies. Now, 30 Doradus, and within it lies the starburst cluster R136, is the closest representative of more distant, high redshifted starburst clusters, or maybe in this, since the last 2 weeks, we've probably called this medium redshift distant galaxies. We see these similar starburst clusters. Now, this whole region, this whole beautiful star-forming region, is powered by around 100 O stars and a few dozen or so Wolf-Rayet stars, which are ionizing the molecular clouds around them. So they can so these create these beautiful arcs that you see in the image, but they also create an immense amount of feedback on the molecular cloud and into the general environment as we speak. Now, at the very heart of 30 Doradus lies the R136 starburst cluster, which I was talking about. And so we zoomed in from a 4-meter telescope image into a Hubble image where you can see R136, the very center. There's active star formation around it, but also in the very core as well. But that's not what we're interested in. We're interested in R136 and the births and deaths of stars within it. So R136, as I've pointed out, contains around 50 to 100 O stars, depending on the radius you use. And in the very central cluster, which is zoomed in here, there's around 50 O stars within a couple of arc seconds. So it's very incredibly dense and very incredibly luminous. So it has around something like 10 to the power 51 photons per second ionizing the clouds around it. And because of this issue, because of the very high dense nature of this issue of the cluster, because of this, you can't particularly resolve the central core. And this creates an issue because you can't resolve the very central stars that are creating this whole region, because you can almost see with the naked eye. And I try to highlight this issue a bit more by showing you a 2 arcsecond field of view in this central cutout, which can be seen here, which hopefully is visible much better to the audience than to me. And so to resolve the very central core, which contains around 50 O stars, you need a resolution of, say, less than 40 milliarcseconds, which is probably the limit to which we can actually see. And the issue in particular is that if you can't resolve the central stars, you can't get their luminosity. And if you can't get their luminosity, you can't estimate their mass very accurately. And you need to know their mass, because mass is the principal factor determining the evolution of the star. And also you need to know the mass to put into a whole host of other things, and also the feedback that is creating this whole region that we see. So the question is probably that if you can't resolve these stars with current instrumentation, do we have to wait for, say, a 30-meter telescope to come and resolve the issues. And as this talk might tell you, it's clearly not, because you can with Zorro. It's stuck. So you can't actually. You can. So you can with Zorro. So this is 2 arcseconds zoomed in to the very first image I showed you. So these stars are responsible for creating that very beautiful, primarily responsible for creating the very beautiful star forming region you see. So the resolution of this image is something better than between 30 to 40 milliarcseconds. And these stars have a limiting magnitude of around 16, so they contain almost all the O stars because of the distance of the large magnitude. They contain almost all the, and the extinction, they contain almost all those stars known within this region. And you can see the scale bar here in the bottom right of 0.5 arcseconds. So if you had that resolution, the central core would completely be unresolved. And marked in this image, you see the stars A1, A2, and A3. And these are very important stars to mankind because they are three of the most massive stars known to us. They're of the spectral type W and H. So they're basically Wolf-Rayet stars. These are so massive and so young that they're still fusing hydrogen inside their core. The N stands for nitrogen, which you can see in the atmosphere, along with some helium. This is due to rotational mixing within the star, but also the mass loss. And also the reason why they were called R136A is because when first spectral imaging was taken of this region, the central core was visible as one object, which is shown as R136A. So you can see how much we've come in leaps and bounds. That's spectral imaging taken in the mid-1980s at LaSIA, and this is spectral imaging taken a year ago at Gemini. So we've come in leaps and bounds, and we can really resolve the core. And you can really see this improvement in angular resolution in comparing with other telescopes. So there lies to the left Hubble Space Telescope images in the UV and the optical, but also infrared images using multi-conjugate adaptive optics in the top center, but also the SPHERE instrument at the VLT both in K-band, and also in the top left, there is a MUSE AO image of the same region. You can say that Zorro is probably comparable or better when you actually look at the resolution, at the measured resolution on the image of the central cutout of the cluster. And you can really resolve A1 from A2 and also A3 from its new companion, which we've just identified using the Zorro imaging, but also A1 from a close by star number 9. So before I dive into why this is actually quite important and why I'm going on about it, we'll go back a little bit to see how massive these stars are. And these stars are extremely massive. So conventionally, based on statistical arguments and also empirical measurements in the Archies cluster in the galactic center and also R136, people have suggested a 150 solar mass limit for the upper end of the stellar initial mass function. Now, Crowther in 2010, using AO IFU spectra and also HST imaging, found that these stars in the very center, or claimed that these stars in the very center of R136 had masses of 300 for A1 and around 200 for A2 and A3. And they followed it up with Hubble SDIS spectroscopy in the UV, and they corroborated that result. And so the HRD of these stars looks something like this. So in the black are the results from Bessel-Lehner, and also in gray are the results from Crowther for A1, A2, and A3. So these stars are extremely massive, all about 150 solar masses. The stellar mass is written there is the stellar initial mass. And they are sort of go against conventional wisdom for how massive stars can go, at least in the nearby universe. But you might have thought of a flaw in the images, because I told you that they used Hubble Space Telescope primarily in 2010, but also they used SPHERE imaging in 2020 to measure the luminosities of the stars. But you can see that the imaging didn't particularly resolve the star 9 from A1, but also A1 from A2 and A3 from its companion. So that meant that actually when we measured the luminosity with Zorro, the luminosity we measured was much lower, or a bit lower. You can visualize that on the SED here. So these are SEDs of A1, A2, and A3. And in red, we plot the Zorro magnitudes, and in blue, we plot the HST and infrared magnitudes. And so this magnitude difference of a few tenths of magnitude actually creates quite a lot different, feeds into a lot of difference in the actual luminosity of the star. And so it turns the HRD, which looks like this, into something like this. So here we have A1, A2, and A3 quite a bit lower than was measured in the literature. And how lower? Well, A1 went from 300 to 250 solar masses from the literature to around slightly less than 200 solar masses. And A2 and A3 sat around 150 solar masses. So we actually have just one star, which is above the canonical 150 solar mass limit. And so what does that actually mean? What are the big results? Firstly, the most massive star known, R136A1, is actually not that massive. And I say not that massive in italics because I mean it in a relative sense. It is still the most massive star known, and it is larger than the canonical stellar mass. The other results, since I'm fast running out of time, we'll skim through them. The first one is the initial mass function. So the IMF is a probability density function, and so you have a lower mass limit where, which is determined by where the core stuff can fuse hydrogen, and also an upper mass limit, which was based on statistical arguments, but also empirical arguments in the nearby universe. The statistical arguments are based on the radiation pressure impairing a star growing any larger, which is around 1,000 solar masses, which is thought to be in the early universe. And in the nearby universe, it was canonically thought to be 150 solar masses. So the result that there was a 300 solar mass star in the nearby universe shifted the upper limit of the IMF considerably. And even though there's a small shift in mass, there's an extremely large shift in the amount of luminosity outputted, because luminosity scales to the power of 3 or higher at this mass end. So there's a lot more luminosity and considerably a lot more mass that's being seen. The most important thing, I think, is the fact that it sort of shows that maybe pair instability supernovae might exist. So pair instability supernovae are hypothesized to be the end product of 150 to 300 solar mass stars. And their importance can't be underestimated, because a single 300 solar mass parent star exploding as a pair instability supernovae releases more metals into the ISM than the complete IMF below it. So these stars are extremely important to understand the evolution of metals. And the hypothesis that these stars greater than 150 solar masses, even the local universe, exist, meant that, okay, we will find pair instability supernovae in the more distant universe. There were other results that do not match the explanation that they exist, but this is the fact that they were 300 solar mass stars suggested that they do, but lowering the upper mass limit lowers the probability that they actually exist. And finally, feedback. So as I discussed, a 300 solar mass star, if you assume a certain IMF slope, say minus 1.95, which is considered okay for 30 Radas, gives out more neutron stars, gives out more neutron star mergers, more black holes than predicted, using the canonical upper mass limit and the canonical IMF. So knowing this upper mass limit is extremely important to predict how many neutron star mergers you can see, how many black holes, all these exotic events that they need a well quantified IMF and also a well quantified upper stellar mass limit to predict. Finally, acknowledgements. I've not gone too in depth into science here, because I thought for the Gemini science meeting it's much more useful for the audience to see a lot more about the data. But if you want to talk about the science, please feel free to email me, message me in the Slack. At GSM, please talk to Ricardo if you're interested in using Zoro. Elliot Horsch contributed significantly to the data reduction and understanding of the data, and he's the chair of the SOC, so please feel free to talk to him about that. Our paper is in press, it's on AstroPay, so feel free to have a look at that. And finally, I will end with a review. Thank you so much for your time.
Thank you very much. There was some beautiful data that you showed. That was exciting. Do we have any questions? Sorry, any questions from the, yeah, we have one there.
Hi, Venu. Thanks for sharing this beautiful presentation, and I really appreciated those zooms from the big sky to the core of R136. So in the work of Crowther, I think the point there, well, the work is very model dependent and assumption dependent. The main conclusion was the masses are not 80 and they're not 1,000. So they came up with 300 saying, yeah, more or less. Then you come with those beautiful Zoro data. And so you seem to be playing in the same range of masses. So my question is, from your appreciation of all the work you did, how much more accurately do you think you have those masses down? Also considering that we have no Keplerian motions, because those don't seem to be binaries, unfortunately. So all we have are luminosities and our very poor understanding of how this relates to the masses.
Yeah, so I don't think we've quantified it in a better range than Crowther at all. That is true. But I think what we have done is resolve the stars in the core. So I think our final result, the take-home result, is probably not the fact that these stars are, say, 100 solar mass lower, and that's written in stone. But I think that we can resolve these individual stars. I'm sure JWST or a bigger telescope will come and resolve it even better. But the actual mass estimate, I mean, it couldn't be. We did some back of the hand calculations based on the central density of the star, central density of the cluster, to see what's the probability of being a binary. And it's not negligible. It's more than 30 to 50% for both A1 and A3. So that also can't be ruled out, but obviously we can't do it with the current data. We can't check if it's actually a very wide orbit binary. I mean, it's unlikely to be a wide orbit binary at these masses, but yeah, to answer your question, we haven't found a mass value that's written in stone. I think that's, yeah.
Well, still, I would be happy to bet a bottle of your favorite thing that it's already merged and it's a single star. Thank you.
Janice, do you have a question?
Hi, Venu. This is Janice. Very, very nice result. And as a person who studies high mass star formation, and this is a really impactful result that will be, I'm sure, the topic of many conversations in our field. My question was actually related. And of course, understanding or constraining the actual masses is very model dependent. But as you said, really the result here is resolving multiple objects and then understanding, having a better constraint on the luminosity, just the observable parameters coming from Zoro. And so doubles in the details. Even with that, there are systematics, 0-point offsets to see what the difference is between your photometry is and the existing photometry. So I just wonder if you could comment on I mean, you had pretty large error bars on the model plots, but in terms of the observable parameters, if there are any issues there that, could be the subject of debate.
Yeah, I think that's the kind of worms, because Zoro is not really built, well, a spectral imaging is not really built for doing this kind of analysis. So I think, I don't know if any paper, maybe Ricardo or Elliot can correct me, but to measure the actual magnitudes, we did we measured at the same air mass a couple of standards, and based on that we got the magnitudes. But that's why the error bars, especially on the blue, are higher.
Hmm.
But this is as well a very unconventional technique to get photometry. So I would be looking forward to JWST imaging, I guess. I mean, it won't get magnitude in this wavelengths, but it would be good to compare it to see the slope of the SED at least. There are a lot of systematics. I think we've tried to answer them more in detail in our paper and to describe it more. But yeah, I think maybe this doesn't fully answer your question, but it's.
Yeah, we
I
can
think there's
continue
not
talking
been
more.
sufficient work done calibrating photometry from a speckle imager at this level to say more about the systematics. Yeah.
Okay,
I
thank
think-
you, and congratulations again on a great
I
result.
think we have to move on. We also have a question, I think it's by Joe Rodinger on Slack. So I encourage you to just to continue the discussion online, and congratulations. That was some beautiful data that you showed there. So let's thank Venu again.